the delay because I was having a little troubles with the StreamYard things here. So sorry for that. Okay, sorry for all the inconvenience caused. So with that hesitation, shall we begin our talk soon? So okay. Okay, so thank you very much for your patience. So I hope that you all are ready for the talks because we are going to begin soon. Okay. Okay, so with that hesitation, let's begin our talk, shall we? Okay, so welcome to True Senses. This it's not sure. This one. So okay, so welcome to my live streaming of this True Senses. This one. Sorry for all the this one. So I hope that if you have any comments, you can feel free to comments down here, and I'll try my best to respond as fast as I can. Okay. Okay. So now let's visualization goes to the talk, shall we? Okay. So as you already know me, some of you. I'm Mr. Chu. I'm from JB. Okay, so I'll cut all the craps in here. Okay, since most of you who are listening to this talk in here knows me quite well already. So I've been teaching since 2003 until now, which is a 19-year experience. I'm also a ex-national trainer for STPM Chemistry. So I also present in many STPM Teknik Menjawab. Nowadays, due to the pandemics, now it's already endemics. I'm giving more live talks like this, okay? But still, if any schools want to invite me over, then you just contact me privately, okay? I will be able to travel. Most of the time now, I'm quite free. I don't have much things with me right now. So if let's say your school want to invite me for Teknik Menjawab face-to-face, I will go to your school and we do a live Teknik Menjawab, okay? Okay, so okay, so let's continue. Okay, so I have written a few books. This is last time the Project A, and then this is the LP published this one, and also published these 3 books. Okay, so now all of them are green color. The yellow color, this one is the old edition. Okay, okay. So like I said, cut out the craps. So now for the scheme of assessment, nothing much really, still the same. 15 objective questions, 2 structure question, and 3 essay question. You have to choose 2 to answer as usual. So nothing much about this one already. So allow me also to skip in here. Okay, so this one also the same. So nothing much also. Okay, so these are the way of how this one assess marks. For SEM 2 ulangan, you should have already no problem already. Okay. Okay, so before examination, so make sure you have read in detail all the chapters of chemistry. If possible, make your own short notes. And if you already buy my module, you'll be able to see end of each module. I provided short notes, but that short notes is not really 100% short notes. You have to add a little bit elements on your own. So make it like your own short notes. Okay, I just provide the base for how to create your own short notes in here. Okay. And then you must do all the past year question from 2013 until 2021. So at least 5 years back, if you can do all 2013 until 2021, which is much more better. Okay. Okay. And then you should also do a group study with your friends and compare the idea, share the idea of how you study things. So shouldn't be much of a problems in here. Okay. Okay, so with that session, let's move on to our talks today. So today we are going to talk about SEM 2 quick revisions. So this one. Okay, so close already. Now I should focus on this one. Okay. Okay, so with ionization, let's continue with this one. Okay, so if you don't have the notes, you can always refer to the notes that I've already share with you through this one. Okay, if you bought my module, you should be able to get these short notes. If not, then you can just listen to the talks first, and then if possible, you get the soft copy or get the hard copy, photocopy from your friend's books or whatsoever. Okay, good afternoon. Okay, good afternoon. Thank you very much. Okay, so the short notes you can get from various resources. So today my talks is based on the short notes that I've already given inside the books already. So I hope that you'll be able to benefit from it, and then we'll see what we can do over here. Okay. Okay, so shall we? Okay. So with ionization, shall we begin? Okay, so I'm going to go quite fast in here. In case if one of you want to ask something, you can always feel free to ask. I will show your comments and then see what I can do about it. Okay. Okay. So let's start off from the this one. Okay. So we start from the thermochemistry. So the thermochemistry, if you have let's say WA plus XB give YC plus ZD, where WA and XB are reactants, YC and ZD are the products. Okay, you can eventually calculate the enthalpy change of reaction. Teacher, wait. Okay, so. Okay, so some of you ask, teacher, what chapter do we have to write phase in the equation? Chapter 1 and chapter 2, okay? Okay, so allow me to continue. Okay, so your enthalpy change of reaction can be written as the enthalpy change, total enthalpy change of the product minus total enthalpy change of the reactants, or Y from the equation YC plus ZD give minus WA plus XD. So in here, stoichiometric coefficient must be taken into considerations when you're doing this. Okay, and then if you are given in terms of certain amount of the mass and product of the substance, okay, so mass or volume of the solution are given with the quantity of the substance reacted. Enthalpy change can be calculated using this formula. Either you can use Q equals to MC theta or Q equals to C theta. So when to use Q equals to MC theta, when to use Q equals to C theta, it depends on the unit given to you in the question. So if the questions give you the unit in terms of joule per gram per degree Celsius or joule per gram per Kelvin, then you use Q equals to MC theta. And M here for our STPM syllabus is mostly water. Okay, then you have to know that 1 centimeter cube of water is representing 1 gram of water. Okay, and then if the unit is given to you in the unit of joule per degree Celsius, this joule per degree Celsius is actually heat capacity of the instrument. So you have to use Q equals to C theta. Okay, Q equals to C theta. Okay, so this is your first step. And then your second step, you calculate the mole of substance. So it can be mass over molar mass of the substance, or it can be MV over 1000. It depends on the situations. So either ones are applicable. And finally, you have your question number 1, which is Q. And then from second equation, you have mole. So if Q is in joule, then it's divided by 1000. So actually, teacher, is it necessarily to leave your answer as kilojoule per mole? Actually, not necessarily. You can leave your answer in joule per mole. The most important thing is number 1, you must be able to make sure that it is either joule per mole. You are written in the correct significant figure. So that is more important than the unit in kilojoule per mole. Okay, so in STPM, we also accept if you leave it in the form of joule per mole, not necessarily kilojoule per mole, unless stated. Okay. Okay, so these are the three basic steps of how you are going to define and calculate enthalpy change of reaction, other than the first formula you use total enthalpy change of the product minus total enthalpy change of the reactants. Okay. Okay, in thermodynamic, when we say a standard condition, it is referring to the condition where we have 25 degrees Celsius or 298 Kelvin at 1 atmosphere, which is 101 kilopascal, and the concentration of the solution is 1.0 mole per decimeter cube. Now, when we say thermodynamic, it actually includes chapter 1 and chapter 2. Okay, chapter 1 and chapter 2. Chapter 1 and chapter 2, thermochemistry and electrochemistry are actually part of the thermodynamic. Okay, so physics students, you should know better because you already learned it, isn't it? In your physics semester 2 or semester 3, I forgot already. Okay, so you should know better. Okay, so let's go to the next one. Okay, so here are all the enthalpy change of the definitions that you need to remember. So list down in here, I have 9. Actually, there are one more, which is bond energy. So bond energy, later you try to find out what is the definition of the bond energy. So you need to memorize what is the definition for enthalpy change of formation, which is the amount of energy change when 1 mole of substance, keyword, 1 mole of substance is formed from its individual element under standard condition. Okay. So you must be able to, sorry, I use highlighter. Okay, so it's the amount of energy change when 1 mole of substance is formed from its element. Okay, its element under standard condition. Okay, so under standard condition. So this one, you must be able to write the full definition. Actually, for all enthalpy change, just finish with the sentence under standard condition. All enthalpy change, just finish with the sentence under standard condition. So don't care whatever definitions you are giving in here. Okay, so for example, if you are trying to write enthalpy change for NaCl, so Na solid plus half Cl2 gas give NaCl. So in here, state of matter is a must. So you must write out the state of matter in thermochemistry and also in electrochemistry. Okay, okay, and then in generally, we say that in enthalpy change of formation, exothermic reaction is more stable than the endothermic reaction. So this one, if you want to understand further, you can always refer to my previous videos where I explain in detail why is it like that. So therefore, the more exothermic the reaction, the more vigorous the reaction, and therefore the more stable the compound form. So that is what the information of enthalpy change of formation can give you in here. Okay. Okay, so that is the first enthalpy change. The second enthalpy change is the enthalpy change of combustion. It is the heat or energy release when 1 mole of substance is burned in excess air under standard condition. Okay, so and the reaction in here is guaranteed an exothermic reaction. So this is example, C2H4 plus 3O2 give 2CO2 plus 2H2O. And actually, in the real situations, if you look at the international reference books, gas is in the combustion of the hydrocarbons, or in the combustion of this one, it is usually in the state of gas. It is actually in the state of gas, but don't mind too much of whether it is liquid or gas, because sometimes even the examiner, the marker also, they sometimes confuse on their own. So as long as you write state of matter liquid, then should be no problem. Okay, but in the real situations, you write as gas. Okay, okay. So this is the second enthalpy change. The third enthalpy change, the enthalpy change of neutralization, is the energy release when 1 mole of hydrogen ion from acid react with 1 mole of hydroxide ion from gas, from alkali, under standard conditions. So this is exothermic reaction. So for strong acid, strong alkali, the enthalpy change of the reaction in here is negative 57.3. So there are some factors that is not equal to negative 57.3. So later, if you want, you can always browse back from my previous video to show why is it not equals to negative 57.3. Okay. Okay. Then we have okay, then the next one is enthalpy change of atomization. Now, this is a standard definition. In a standard definition, it is the energy absorbed. Okay, it is the energy absorbed. Okay, it is the energy absorbed when 1 mole of gaseous atom is formed from its element. So this is under a standard definition. Okay, a standard definition is 1 mole of gaseous atom formed from its element. So for example, half of the bromine liquid give bromine gas. Okay, so this is the standard definitions of the atomizations in here. Okay. Okay, and this process is an endothermic process. This process is an endothermic process. Okay, so atomization can also be in the form of molecule. So in the form of molecule, it is the energy absorbed when 1 mole of compound is burned to form is atomized to form a gaseous atom. Okay, is atomized to form gaseous atom under standard condition. Okay, so that is if the question asks about enthalpy change of atomization. Of course, enthalpy change of atomization involving molecule is involving compound. Involving compound is no longer a standard definitions already. Okay. Okay, then we have ionization energy. So ionization energy is the energy absorbed when 1 mole of electron is removed from a gaseous atom to form a unipositive charge ion. Is not important. The most important key in here, 1 mole energy absorbed, 1 mole electron removed, gaseous atom. Okay, so under standard condition. Okay, again, the process in here is endothermic. Example of equation: A gas give A plus gas plus E minus. Okay, okay. Now, if you have any questions, you can straight away ask. I have no problem. If no, then I will just keep on discussing. Okay. Okay. Then the sixth enthalpy change of reaction that you need to define in here is the electron affinity. So electron affinity is the energy releaser when 1 mole of electron is received from by a gaseous atom to form a uninegative charge ion under standard condition. So this one is the standard definition for the electron affinity. So X gas plus E minus give X minus gas. First electron affinity is exothermic. Second electron affinity is endothermic. Okay, first electron affinity is exothermic. Second electron affinity is endothermic. Okay, so why is it like that? You can always go back to this one. So don't forget, today is an express class to highlight what are the 7 topics that you need to know on which one to study. Okay. Then we have lattice energy. So what is the lattice energy? It is the energy released when 1 mole of solid crystal lattice is formed from oppositely charged gaseous ion. So in here, 1 mole is stressed on the crystal solid lattice form. So it must be solid. And then which is formed from oppositely charged gaseous ion. Oppositely charged gaseous ion. So again, lattice energy is guaranteed an exothermic process. Okay, lattice energy is guaranteed an exothermic process in here. Okay, and the factors influencing the lattice energy is directly proportional to the charge. Okay, inter-ionic charge, yet inversely proportional to the inter-ionic radius. Okay, so that is for enthalpy change of the lattice energy. And then for hydration is the energy liberated or energy released when 1 mole of gaseous ion is dissolved in water to form aqueous ionic solution under standard condition. Okay, so in the hydration, the factors that influence the enthalpy change of the hydration is actually the same with this one, where we say that enthalpy change of hydration is directly proportional to the charge, yet inversely proportional to the inter-ionic radius in here. But different from the lattice energy, the hydration is individually looking at the cation and anion, while in lattice energy, it is looking at both ion together. So that is the differences between the factors influencing the lattice energy and also hydration. Again, I repeat, for lattice energy, we look together positive ion, negative ion together. But for hydration, they are individual. That means cation has its own hydration, anion has its own hydration. Okay, so that is the difference between the lattice energy and also hydrations in here. Okay. Okay, so teacher, is water necessarily to be written in the equation or not? Actually, no need. Water is not necessarily to be written in the equation. No need. Okay, just write the changes of the state of matter from gas to become aqueous. Okay, so that is more important in here. Okay, okay, so that is for enthalpy change of the hydration. And last but not least, enthalpy change of solution. So in enthalpy change of solution, it is the energy change when occur when 1 mole of solute is dissolved in excess water to form an infinite dilute aqueous solution. Okay, so when the process is endothermic, where we said lattice energy is greater than the hydration, we said that the salt is insoluble in water, whereas in the exothermic process, where the lattice energy is smaller than the hydration, then the salt is soluble in water. So this is the significance when enthalpy change of solution is endothermic and exothermic in here. Okay, okay, so okay, good afternoon, William. Okay, so then in here, the key in here is how solid become aqueous solution with the opposite charge ion. Usually they ask in terms of the ions in here. So they won't give covalent compound. Covalent compound solution is not really inside this one. I see, wait, okay, this one. Okay, I've seen some answer scheme for trial paper says lattice energy is energy absorbed. No. Lattice energy is guaranteed energy release. Okay, so you can always, if anything it tells you, you always Google or you refer to the international reference books. Okay, those are the most accurate one. Lattice energy is the heat energy release. Okay, so if let's say they really comes up some absorbed, then it is not lattice energy. It is a reverse of lattice energy. Okay. Okay, good afternoon, Tak Chan. Okay, so that is all for the 9 definition of enthalpy change that you all must be able to remember. You have to know how to define all these, please. Okay, okay, so with that, that is for the enthalpy change. Okay, so any else questions before we move on to the next one? Okay, so if no problem, then we go to the next one. Okay, so the next one in here shall be okay, Hex Law. Okay, so you must know how to define Hex Law. Hex Law is defined as the following. Please remember to highlight these 2 keywords. Is it enthalpy change of a chemical reaction is the same. This is the first keyword. Enthalpy change of a chemical reaction is the same. First keyword. Second keyword is regardless of the route taken in single step or series of steps. Some books write regardless of the route taken, or some books write no matter it is in one step or series of steps. So no matter which one that you want to use for your definitions, all of them are acceptable. Okay, they bring the same meanings in here. But the 2 keywords that you must highlight is number 1, enthalpy change of a chemical reaction is the same, number 1. Number 2, regardless of the reaction take place in one step or series of steps. So that is the 2 very important keyword definitions for Hex Law in here. Okay. Okay, so in here I can only show you 1 example. In the short notes, I only shows you 1 example. If you want to find out more examples, you can always browse back to my YouTube video. What am I trying to highlight from here is, now in essay question especially here, essay question when they contain a lot of marks, let's say 6, 7, 8 marks, that require you to apply Hex Law. Here are the technique of how you should apply. Number 1, let's say if the questions wants you to calculate this equation, and they give you all enthalpy change of atomization. Now in STPM, they won't give you this equation. This equation you have to write on your own. Let's say they give you atomization of the CH3Cl. Okay, so you have to write on your own. What is the atomization of the CH3Cl? Okay, so for example, okay, if CH3Cl, you have the atomization, for example, okay, CH3Cl gas atomized to become carbon gas plus 3 hydrogen gas plus chlorine gas. If CH3 atomized, then you become carbon gas plus 3H gas. Then if chlorine atomized, half chlorine gives Cl. Please remember by heart that elements, the enthalpy change of atomization is standard. That means at the end of the day, you only form 1 gaseous atom. Okay, you only form 1 gaseous atom. Okay. Okay, so this is something that I would like to highlight using this example. And then in STPM 2013 ulangan, 2014 ulangan, 2014 itself, 2016, 2018, a lot of years asked using Hex Law. So the safest way to apply Hex Law is you have to write out equations by equations in here. Okay, and then because you want to find out this equation, isn't it? So you have to learn on how to apply the Hex Law. So from here, you have to do the this one. So you reverse equation 1, no need to do anything. Then equation 2, you need to reverse. Okay, you need to reverse equation 2. And then equation 3, you multiply by 2. So when you redo all the equation, you write back the equation. So yeah, CH3Cl gas plus C plus 3H plus Cl, then C gas plus 3H gas gives CH3. So when you reverse, the sign become opposite already. Magnitude is still the same. And then in here, originally is 1 chlorine. So now because you want to form Cl2, so you use 2 chlorine and it is reverse. So as a result, you can start to cancel in between things already. So what you can cancel, you can see from here, you cancel carbon with carbon, you cancel hydrogen with hydrogen. So at the end of the day, what do you have? You have CH3Cl reacting with 1 Cl gas, give a CH3 gas plus a Cl gas, Cl2 gas. So teacher, what is the single dot in here? This single dot in here is radical. So radical is single electron. So teacher, will single electron influence the enthalpy change of the reaction? No. Because according to the energy law of conservation, only substance has mass will changes. Electron, even though it has mass, but its mass is negligible. So that is why even with the presence of the radical, it will not influence much the enthalpy change of the reactions in here. So that is why we can ignore the radicals in terms of the enthalpy change. But still, in your overall equation, you must include this one. Okay. So this is in terms of the Hess cycle. Now, how to draw energy level diagram? I have received many questions from various students that says that books sometimes use this cycle, sometimes use that cycle. I don't know where. I to be honest, I only know one cycle. The only cycle that I know in here is the cycle that I'm going to show you, which is this one. Okay, this is sometimes called as Hess cycle, sometimes called as energy cycle. Whatever it is, my advice to all of you, you only use this cycle, because in this cycle, it is balanced. It is balanced in terms of energy and balance in terms of atoms. Okay, so you see in here for each energy levels that I illustrated in here. So if you look at the total left side and the total right side, so do you still, if you still remember what is the definition of enthalpy change of the reaction? Enthalpy change of the reaction says that energy Hex Law says that enthalpy change of reaction is the same no matter the reaction take one step or series of steps. So this is the one step in here. So this is the series of steps. Do you see that? So it is to say that enthalpy change is the same. Okay, so that is why using this cycle is the most safest way. So how to draw this cycle? I'm so sorry, because of the time constraint, I won't be able to discuss all the cycle. If you want to learn on how to draw the cycle, you can make use of my module. You refer to the YouTube, or even if you don't have my module, you can also refer to my YouTube. I've shown you many examples of how you draw the cycles, so you might want to look back on your own, please. Okay, so that is what I can advise you for the cycles in here. Okay, so I hope that you understand that. Okay, so far, any questions that you want to ask before we move on to the next one? Okay, so if no problem, then we move on to our next this one, shall we? So is a cycle similar to Born-Haber cycle? Born-Haber cycle is another story. Later we will discuss Born-Haber cycle. Don't worry. Okay. Okay, and then this is the relationship between enthalpy change of solution with hydration and lattice energy, where their relationship in here is enthalpy change of solution is equals to enthalpy change of hydration minus lattice energy. Okay, so in here I've already summarized in the form of table. When does the enthalpy change of the solution is endo? When is the enthalpy change of solution is exo? Okay, so when is the enthalpy change of solution is endo? Is when your lattice energy is greater than that of the hydration. So when your hydration is smaller, you see because it is hydration minus lattice energy. So if your enthalpy change of hydration is smaller, lattice energy is greater. Actually, it's not plus plus. Sorry, I accidentally put the wrong symbol. It's actually minus negative. Minus negative. Okay, minus negative. So minus negative will eventually become plus. So when you have a plus number minus with a smaller number, so your overall in here will be positive. Okay. So what is the significance in terms of the solubility? So in terms of solubility, when we say that enthalpy change of solution is endothermic, most of the solute are sparingly soluble in water. Okay, so that is what the significance when the enthalpy change of solution is endothermic, except for the sodium, potassium, and ammonium salt. Okay, so they are all endothermic. They are all soluble salts. Okay, so why are they soluble? You can find out on your own, but don't have to really purposely memorize on that. Okay. Okay, so in terms of the Hex cycle, so you draw accordingly because showing to you in here this one, this is your okay, so this is your lattice energy. So where if you look at the cycle carefully, okay, so this is your lattice energy, and this is your enthalpy change of the hydration. Okay. So when your lattice energy is much more exothermic compared to the hydration, so that is why this is your solution. So your solution is endothermic in here. Okay. Okay. So that is what happened for Hex cycles in here. Okay. Okay. Then this is the first one. Sorry. Okay. Then you have for the second one. Okay, so for the second one, okay, so when does the enthalpy change of solution is exothermic is when your hydration is greater than that of the lattice energy. So when your solution is hydration is greater than the lattice energy, that means the salt are very, very soluble in water. Okay, so high hydration energy indicates that the ions are strongly attracted to water, while low lattice energy indicates that attraction forces between the cation and ion are not strong. So that is why they are easily soluble in water, hence dissolve inside water. So that is why when your enthalpy change of solution is exothermic, when we say hydration is greater than the lattice energy, so most of the solute are soluble inside water. Okay, so this is the energy cycle that you have to use whenever you are trying to describe the solutions in here, where you have this is the hydration. Okay, this is the hydration, and this is the lattice energy. Okay, and this is the solution. Okay. Okay, so I even have examples inside the YouTube, so you can rewatch my channels if you want a quick revisions on the examples of how you apply the this Hex cycle for the reactions in here. Okay. Okay, so that is for the solution hydration and also the lattice energy. Okay. Okay, any questions that you want to ask before we move on? Okay, so hopefully not much of a problem. If not much of a problem, immediately we move to the next topic. So the next topic that as you want to discuss right now is the Born-Haber cycle. Okay, so for Born-Haber cycle, this is the only way to draw Born-Haber cycle. I don't know where else you have seen people draw Born-Haber cycle, but under my classes, there is only one Born-Haber cycle, which is the one that I'm about to show you. Okay, so to construct a Born-Haber cycle, they have structure. So just follow the structure, then you'll be able to draw a perfect Born-Haber cycle. Okay, so the first step is by drawing the enthalpy change of formation for the reaction. And in STPM, they actually insisted that this one you must put as 0. Starting from the formation here, you must put at 0 from the reactant to the product. Okay, and then always remember to label your y-axis as energy. Every time when you draw an energy level diagram, you must always have energy label in the y y-axis in here in kilojoule lah. Okay, so this one is always a must. Students tend to neglect this fact in here. Okay, so this one must always draw. Okay, okay. Then after you draw the formation, then you start to draw one by one, starting from the atomization of sodium, then first ionization energy of sodium, okay, atomization of chlorine, electron affinity of chlorine, okay, and then the lattice energy of the chlorine in here. So I have inside my YouTube slide, I show various examples about how to draw a Born-Haber cycle. So you might want to find out on how to draw. So try to find out on your own. Okay, and then how to calculate lattice energy. The formula to calculate lattice energy, there is only one, which is enthalpy change of the formation is equals to hydration plus the summation of everything. If you still remember definition of Hex Law, Hex Law state what? Hex Law state that enthalpy change of the reaction is the same no matter the reaction take one step or series of steps. So where does the series of steps goes by? The series of steps goes by summation of atomization, ionization energy, atomization of chlorine, electron affinity of the Cl. So you see or not? No matter reaction take one step or series of steps. So Born-Haber cycle in here is actually applying the Hex Law inside here. So that is why this formula is always the correct formula. Okay. So our formula is enthalpy change of formation is equals to lattice energy plus the summation of everything inside there. Okay. Okay, so after you do that, you substitute all the values given to you inside the data booklet, inside the question. And then you'll be able to calculate lattice energy accordingly in here. Okay, so for more examples of the lattice energy on how to construct them, so I hope that you go and explore on your own via various resources. There are many resources nowadays you can activate too. So this is how you are going to this one. Okay. Okay, so any questions else before we move on to our next topic? So that is all for chapter 1 that I would like to highlight. Okay, any question for chapter 1? Okay, so if no problem, then we go to chapter 2, shall we? Okay, so let's go to chapter 2. Okay, so in electrochemistry and electrolysis, so you introductions towards oxidation reduction, actually not very important, okay, but still some of the basic of the electrochemistry you must try your best to remember, especially what happened during oxidation. Oxidation is a process where the oxidation state of a species has increased by donating electron. So inside your half equations, when you know that it is oxidation, automatically electron is at the right hand side of the equation. Okay, so when we say that we remove electron, that is an oxidation process. Okay, so that is why quickly write electron at the right hand side. Okay, so for example, Na solid give Na plus plus E minus. Okay, so oxidation state changes from 0 to become +1. Okay, and then another example, Pb2 plus oxidized to become Pb4 plus plus 2E minus. Okay, so at the same time, the electron is at the right hand side of the equations in here. So how to write all these simple half equations? Inside my module, I also explain step by step of how you do that. So if you want to find out more, you can always refer to the YouTube of how I teaches you one by one, okay, on how to write the half equation. So you better get to know how to this one. Okay, very good, Wenxuan. I hope that you can understand us. Okay, then we have reduction. Reduction is the process where the oxidation state decreases by accepting electron. So the moment that you know that it's accepting electron, quickly write an arrow, okay, electron put at the left hand side of the equation. Okay, so this is the inside a chemical equation. This is where you say that reduction reaction take place. Okay, where electron is put at the left hand side of the equation. Okay. Okay, so for example, Cu2 plus plus 3 minus gives Cu, Fe3 plus plus E minus give Fe. So these are the examples of the reduction equation. Okay. Okay, so that is a little bit introduction. By the way, substance, the species that undergo oxidation is also known as a reducing agent. The species that undergoes reduction is also known as an oxidizing agent. So in this case, sodium is a reducing agent. Lead-2 ion is a reducing agent, whereas in this case, copper is an copper 2 plus is an oxidizing agent. Fe3 plus is an oxidizing agent. Okay, so that is what it means in here. So when the species undergoes oxidation, it is at the same time becoming a oxidizing agent in here. Okay, so that is how you are going to this one. Okay. Okay, so that is for number one. Okay, then here are the step-by-step of how to construct a balanced half equation, calculate the oxidation state for both reactant and product. So from the difference of oxidation state, so if the oxidation state increase, electron quickly put at the right-hand side of the equation means that the electron are donated. If the oxidation state decrease, electron quickly put at the left-hand side of the equation showing that electrons is received. Then balance the number of atoms other than oxygen on both sides. So number 4, based on the different oxidation state and number of atoms, the number of electrons donate and receive are few. Okay, so if the data, and if you want to see more examples, you can always go to my YouTube to find out more. Okay, third, balance the number of oxygen atom at both sides of the equation using water, which the side with the less atom of oxygen. So let's say initially your left side contains 2 oxygen, your right side has no oxygen. So you add up these 2 H2O at the right hand side of the equations in here. Okay. So you add up this H2O, 2O inside the right hand side of the equation. So after you balance the 2 H2O, so you counterbalance the number of the hydrogen ion in water. Because now you have 2 H2O at the same time you have 2 H2. So you counter with H plus at the opposite side. Okay, so it depends on the substance. Sometimes it may be more, sometimes it may be less, sometimes it may be balanced on its own already the moment that you add water. So count every atoms accordingly, and definitely you're able to get it correctly. Okay, so that is how you balance the ionic equations. Okay, so these are examples of how I show you step by step. For example, ClO3 to ClO5. So the difference of oxidation state is from +5 to become -1. So from +5 to -1, so it is a reduction. So if it is a reduction, quickly electron put at the left-hand side. So the difference from +5 to become -1 is equals to 6 electron. Okay, so 6 electron, quickly put 6 at the left-hand side in here. Okay, then you see in here, ClO3 here has 0 O, no O, isn't it? So you put 3 H2O at the right-hand side of the equation. So when you put 3 H2O, that is at the moment that you have 3 H2, isn't it? So that is the moment when you have 3 H2. So when you have 3 H2, you balance with the 6 H plus in here. So with that, that is how you write the balance equations in here. Okay, so this is the example of half equation involving a reduction. And then what about oxidation? So for example, in here, you have Cl2O4, Cl2O2 minus to Cl2O4 2 minus. So this one is from +3 to become +6. Okay, so it is an oxidation process. So when it is oxidation process, quickly electron put at the right hand side. So balance the atom first, 1 chromium, 1 chromium. And since from +3 to +6, it changes by 3 oxidation state. So you put here 3 electrons. Do you see that? Okay, then you okay, and then in the left hand side has 2O, right hand side has 4O. Do you see that? So you balance up the atoms with 2 H2O. Okay, and when you have 2 H2, that is at the same time when you have hydrogens in here. So when you have hydrogens in here, you must counterbalance the hydrogens in here by placing with the hydrogen ion. Okay, so with that, that is how you write a balanced ionic equations in here. Okay, so for more examples, you can always refer to the YouTube that I have various examples for you to refer to in here. Okay, so that is how we write half equations. And then right after you balance the half equation, eventually you need to know on how to write the overall equation. So we use the oxidation and reduction half equation just now. So the key in here is you have to first balance the number of electrons. So since in here you donated 3 electrons, in here you receive 6 electrons, you find the lowest common multiple in between oxidation and reduction half equation. So lowest common multiple between 3 and 6 is 6. So the whole equation in the oxidation half equation in here, you multiply by 2. Okay, so when you multiply by 2 this half equation, so this one no need to do anything. So everything will be multiplied by 2 lah. So that is where you have 4, that is where you have 2, that is where you have 8, okay, that is where you have 2, that is where you have 6. So the first thing that you must be able to cancel out in between these two equations is the number of electrons, because how many electrons accept that is how many electrons receive. Okay, what else can be cancelled? If you notice carefully here, 4 H2O cancel with 3 H2O. Do you see that? You cancel lah. Okay. Then here got 8 H plus. Here got 6 H plus. So how many H plus remain? You have 2 H plus remain. Okay. So that is how you balance. So as a result, the overall balance equation is H2O plus 2 ClO2 minus plus ClO3 minus give 2H plus 2 ClO4 2 minus plus Cl minus. So that is how you are going to write overall ionic equation based on the oxidation and reduction half equations. Okay. Okay. So any questions that you want to ask about oxidation and reduction half equations? So this is the safest method for you to know on how to write the equations in here. Okay. Okay, so for more examples, you can always refer to the YouTube from my other videos so that you can see more details. Okay. Okay, so with ionization, let's move on to the next one, shall we? Okay, so the next one is disproportionation. So what is the disproportionation? Disproportionation is a reaction where oxidation and reduction occur simultaneously on the substance. All these equations, eventually you must memorize them. You eventually learn how to memorize them at the end of the day. So try your best to remember them. Okay, so you must be able to propose which species is acting disproportionately. Okay, so here are some examples. Okay. Okay, so any questions for balancing half equation and disproportionation reactions? Okay, so if no problem, then we are going to go to the next subtopic. The next subtopic is how do we measure the standard electrode potential? How do we measure standard electrode potential? So the methods of measuring standard electrode potential are very, very standard. So you must compare next to a standard hydrogen electrode. So this is a standard hydrogen electrode in here. Okay. Showing to you in this diagram, this is a standard hydrogen electrode where you must label hydrogen gas, 1 atmosphere go in, the hydrogen ion at 1 mole per decimeter cube, 25 degrees Celsius. So platinum in here is used as the electrodes in here, okay, connected via a salt bridge, okay, to the species that you want to study. So let's say if you want to study the electrode potential in between Zn2 plus Zn, okay, Zn2 plus Zn. So in here, you use zinc plate. So this is your zinc plate, okay, immersed inside zinc 2 plus in 1.0 mole per decimeter cube. So this is a very, very standard setup in between metal ion aqueous solution. Metal ion aqueous solutions in here. Okay. So usually in STPM, they will give you this E naught value. E naught value of Zn2 plus Zn is negative 0.76. The question usually will ask you to describe how you measure this negative 0.76. Okay. Now inside here, because this is a chemical cell. Inside a chemical cell, the electromotive forces will always be positive. In a chemical cell, electromotive forces will always be positive. So don't be surprised in the diagram in here, you have to write out as positive 0.76. Okay, but then you can see that where the diffraction of needles goes to. So the moment that you know that the value in the E naught here is negative, that means Z in here will act to oxidize. Okay, Z in here will act to oxidize, and then the standard hydrogen electron in here will act to reduce. Okay, so the flow of electron goes from the zinc to the hydrogen electrode. Okay, so that is how you know that which species undergo oxidation, which species undergoes reduction. In short, I'm going to say like that. If the question gives you E naught value is negative, E naught value of X plus to become X, okay? Okay, so this X plus will act as the anode, okay? Whereas the standard hydrogen electrode will be the cathode. Okay, so this is how they are going to be, okay? What else? Okay, then conversely, if the standard electrode potential in here is positive, okay? Conversely, if the standard electrode potential in here is positive, for example, copper, so you know that this X plus in here will act as the cathode, where the SHE will act as the anode, okay? So everything when it acts as the anode, it will undergoes, anything that you know that it acts as the anode, it will undergoes oxidation process. Everything that acts as the cathode will undergoes a reduction reaction, okay? So this is the half equation occur at anode and cathode in here, okay? So you must be able to write down the half equation together with state of matter. State of matter is a must when you try to express this. Okay, so and then you try to write the overall equations in here, okay, together with the state of matter. And then you must be also be able to tell on how to write the cell diagram. Cell diagram is this is two line. Two line in here actually represents salt bridge. Okay. Okay, everything at the left side is for oxidation. Everything at the right side is for reductions. Okay, so this rule will never change no matter what. Okay, so therefore zinc will oxidize to become zinc 2 plus from the this one. Hydrogen ion will accept the electron to form hydrogen gas, and then through the platinum, okay, the electron will keep on flowing back, okay, like this. So this is how the electron flow scheme, that's why sometimes we call this as a cell diagram, because through this one sentence, you'll be able to tell how does the flow of electrons go, okay? Okay, then how do we get the E naught value equals to negative 0.76? So because we have E naught cell equals to E naught cathode minus E naught anode, okay? In this case, our standard electrode potential is guaranteed positive. Standard electrode, our chemical cell is guaranteed a positive. So positive 0.76 is equals to E cathode minus E anode. So since hydrogen is the cathode, so E naught value for the cathode is always equals to 0. Okay, for the standard hydrogen electrode, E naught value is always 0. So 0 minus E anode is equals to positive 0.76. That is why the E anode in here is negative 0.76. And this is therefore, by the conclusion, how zinc becomes zinc 2 plus 3 minus gives Zn, E naught is negative 0.76. Okay, so this is how you are going to describe how do you become the how do you making use of the standard hydrogen electrode to deduce the electrode potential of a substance species. Okay, can understand. Okay, so you must be able to describe all of this. Okay, any questions so far? Which part in here they cannot understand? Would like me to repeat for you? So hopefully not much of a problem, because they are actually quite basic, and the STPM asked 1 or 2 times already how to make use of the standard hydrogen electrode to describe the standard electrode potential in here. Okay. Okay, so no problem. Then we move on to the next one. This is how you set up between a non-metal ion aqua solution, for example, fluorine and fluorine gas. And this is what happens when you set up a mixture of the metal ion at different oxidation state. I would like to highlight in here, in the mixture of ion at different oxidation state, you use platinum as the electrodes in here. And then only then you have the mixture of the For example, chromium 3 plus, chromium 2 plus at the concentration 1.0 mole per decimeter cube in here. Okay, when you are describing what happened at anode, cathode, how to write the cell diagram, how do you determine the standard electrode potential. So all of them are similar to what I help you to describe in here. So in another word, you must be able to describe all of them whenever you are trying to explain how do you measure the standard electrode potential of the substance involved in here. Okay. Okay, so that is how we deduce the standard electrode potential. Okay. Okay. Any questions before we move on to the next one? Okay, so I hope that not much of the questions. Okay. Okay, so if not much of a question, then immediately we move on to the next one. So the next one is what does this E0 value can tells you? E0 values can tells you from the standard electrode potential. What does it mean by positive, negative? Okay, in E0 value, if E0 value is positive, okay, we say that equilibrium favor. When we say E0 value is positive, equilibrium favor to the forward reaction. Okay, so when it is positive, so equilibrium favor to the forward reaction. That means it loves to undergo reduction. It loves to undergo reduction. Okay. Therefore, at the same time, when you love to undergo reduction, okay, therefore you are more likely to become an oxidizing agent. Oxidizing agent. Okay. Conversely, when you have the E0 value which is negative, okay, if the E0 value is negative, it indicates that equilibrium favor to a backward reactions. Okay, that means you love to undergo backward reaction. Now, in our standard electrode potential, all of our half equation is written in the reduction form. So when you want, when you are negative, you like to go backward. That means that you are more readily to undergo oxidations. Okay, so at the same time, the species here, M in here, will act as the reducing agent. Okay, so how do we compare the strength of oxidizing and reducing agent? So it depends on the E0 values in here. So let's say given to you, E0 value of the F2, F minus and Cl2, Cl minus are positive 2.86 and 1.36 respectively. So from here, we can eventually tell that F2, F minus is more positive than Cl2, Cl minus. Therefore, we say that fluorine is the stronger oxidizing agent than chlorine. Okay. So in other words, if let's say you are given the two half equations for the fluorine here. Let's say when you have F2 plus 3 minus, okay, give 2F minus, okay. And then you have Cl2 plus 3 minus, give 2Cl minus, okay. So in other words, in here, because we are looking for oxidizing agent. So when you are looking for oxidizing agent, we choose the one which is more positive or less negative, more positive or less negative. Okay, then that species will act as a stronger oxidizing agent. So once you choose that, choose the species at the left-hand side of the equation. So in this case, fluorine will act as a stronger oxidizing agent. Okay. Okay. Whereas in terms of reducing agent, okay, so at first, for example, E0 lithium plus lithium and Na plus Na is negative 0.35 and negative 2.71 respectively. So in another word, when we try to write for the, you see, right, Li plus E minus give Li, okay. E0 in here is equals to negative 0.35. 3.05, sorry, 3.05. And then at the same time, we have Na plus E minus. Na plus E minus give Na. Okay, E0 values in here is negative 2.71. So when we have 3.05 and 2.71, so we know that this half equation is going to be a stronger reducing agent. So the moment that you want to deduce the reducing agent, you look at the species at the right. So in this case, lithium is a stronger reducing agent. Okay, so in short, we say that if you want to choose for a stronger reducing agent, you look for the most negative or the least positive inert value, then you look at the species at the right. Okay, so that is how you are going to choose for oxidizing agent. Okay. Okay, so is there any questions that you want to ask about oxidizing agent and reducing agent? Okay, so if no problem, then we move on to the next one. Huh? Okay, so sorry, because I got some disturbance image on my slide in here, which I need to delete first. Sorry, because it looks very, very messy. If you've got all these things inside here. Sorry, I didn't notice about that before. Give me like 1 minute. Need all these messy things that you have inside the slide here. Some of them can be quite hindrance. Sorry, I need to remove a little bit. Okay, sorry, give me 1 minute. I remove all this. Okay, so shall we continue? Okay, so now how do you, from a chemical cell, determine which one is an oxidizing agent, which one is a reducing agent in here? Sorry, which one is the anode, which one is the cathode in here? So the way of how we tell which one is the anode, which one is the cathode, you can tell by using the inert values. You can tell by using the inert values in here. Okay. So how to choose between anode and cathode in a chemical cell? It goes like this. To become the anode of the cell, the standard electrode potential must have a more negative or less positive value. So because anode undergoes oxidations, whereas cathode undergoes reduction. So when you have the inert value more negative, that means it loves more to undergoes oxidation reaction. So therefore, it becomes anode of the cell. Okay. And conversely, if you have the inert value which is less negative or more positive, then you act as the cathode of the cell. So maybe if I just say like this, you won't be able to understand. So why don't we make use of the examples to tell you on how to read which one is the anode, which one is the cathode. Okay. Now showing to you in here, if let's say you were given the standard electrode potential in between Zn2 plus, Zn and Cu2 plus Cu in here. Okay, so Zn has the inert value of negative 0.76, Cu2 plus Cu is positive 0.34. So in another word, more negative will act as the anode of the cell, whereas more positive will act as the cathode of the cell. So since inert value of the Zn2 plus Zn is more negative, while Cu2 plus Cu is positive, therefore Zn2 plus Zn will undergo oxidation, while Cu2 plus Cu will undergo reduction. So this is the oxidation and reduction half equation in between zinc and also copper. And therefore, when you compare, you cancel electron and electron. So you do it like a Hex Law method. At the end of the day, you sum them up. So as the result, the overall equation in here is Zn solid plus Cu2 plus gives Cu solid plus Zn2 plus. Inert cell is equals to positive 1.10. Okay, and based on the half equation, you are able to write the cell diagram. So the cell diagram is, still remember, if you have double line in here, which is the salt bridge. Okay, so everything on the left side in here is for oxidation, and everything at the right side in here is for the reduction. So Zn oxidized to become Zn2 plus through salt bridge electron transfer, and when you have Cu2 plus to Cu. Okay, so that is how you're going to write the cell diagram. Okay, and then another example, let's say Br2 plus 3 minus give 2 Br minus, Fe3 plus 3 minus plus E minus give Fe2 plus. But now you will notice in here, both of the E0 values in here is positive, isn't it? How do we, if both of them are positive, how do we determine which one is anode, which one is cathode? So keep remembering the rules. The rules in here says that the more positive E0 value will become the cathode of the cell. So therefore, this is the cathode. Okay, the one with the less positive E0 value will become the anode of the cell. So therefore, Fe3 plus Fe is the anode of the cell. Okay, so here is the oxidation and reduction half equation. So oxidation, so Fe2 plus give Fe3 plus E minus, E0 is negative 0.77, and then Br2 plus 3 minus give 2 Br minus, E0 is positive 1.06. So the overall equation is written like this, and you calculate your E0 cell is equals to positive 0.30 volt. Okay, so based on the half equation and the overall equation, the cell diagram can be written as such follow. Okay, so this is the way of how you tell inside a chemical cell which one act as the cathode, which one act as the anode of the cells in here. Okay, so that is how the reactions goes. Okay, okay. Is there any questions that you want to ask before we move on to the next one? Okay, so hopefully my explanation is clear enough for you so far. So let's together have a look at the next one. Okay, so now is another story. Just now this is a chemical cell, isn't it? Where inside this chemical cell, you can see that both of the half cell are separated in here. Now, when we discuss a spontaneity of a chemical reaction, what we are doing is we are mixing both of the substance together. When we are mixing both of the substance together, we have to deduce, we have to explain whether a reaction can take place or not, or the reaction does not take place in here. Okay, so how to deduce whether a reaction take place or whether a reaction will not take place will depend on the E0 values in here. Now, when deducing spontaneity of a chemical reaction, E0 cell can be negative. E0 cell can be negative. Okay, so what is going on? Let's have a look together. Now, when deducing the spontaneity of a chemical reaction, so based on the E0 cell calculated, so we can predict whether a reaction is will take place or not. Okay, so if the E0 cell of a reaction is positive, we say that the reaction is spontaneous. Therefore, a chemical reaction will take place to form the respective product. And conversely, if the E0 cell of a reaction is negative, we say that the reaction is non-spontaneous. Therefore, a chemical reaction will not take place and no product will be formed. Okay, so the key to determine in the suitable standard electrode potential, hence the E0 values are described below. So number one, you must be able to recognize the reactant take place. So since substance may be in salt, so it is important for you to understand which species is actually involved. So mediums such as K+, Na+, SO4 2- F- are usually not taking part in the reactions. So usually it is the opposite salt. They will undergo the reactions in there. Okay, and write out the two standard electrode potential involving the reaction. So make sure that both position must be opposite. In another word, one of the half equation is doing oxidation, another half equation is doing reductions. Only then you can able to compare. So in here I give you one or two examples. If you want to form more example, you can go to my examples there to see in more details. Okay. Okay, so for example, if we say chlorine gas bubble into a titanium, okay, if chlorine gas bubble into a titanium, okay, so our reactant in here is chlorine gas and titanium, and if you look at the standard electrode potential in here, so this is the half equation where chlorine is doing an oxidation, so Cl2 give plus 2H2O gives 2HOCl plus 2H plus 3-, so E0 is negative 1.64, whereas Ti3 plus E- give Ti2 plus, E0 is equals to negative 0.37. So overall equation, you compare accordingly and then you write down accordingly. Eventually, you find out that E0 cell is negative 2.01 volt. So in here we say that since the E0 cell is negative, so we say that the reaction is non-spontaneous. That means the moment you dissolve chlorine inside the Ti3 plus, so it will not be able to react inside there. Okay. Okay, then another example is now what happens when potassium iodide is added to the potassium manganate. Okay, what happens if potassium iodide is added to potassium manganate in here? Now, student, you must be very good in telling what is the species that is reacting. So this is potassium iodide is Ki, correct? Okay, and then potassium manganate is KMnO4. Okay, so when in between the two species in here, which one actually you are reacting? K cannot be involved in the reaction. So the two species that is reacting is actually I minus and MnO4 minus. So you look at the reactant which contain I minus and MnO4 minus inside your standard electrode potential. Okay, then you compare accordingly. So 2I minus give I2 plus 2E minus. That means ion is doing oxidation. MnO4 minus is doing reduction. Okay. So when you write the overall equation, you get your E0 cell to be positive 0.98. And since E0 cell is positive, then you say that the reaction is spontaneous. In other words, if you add KMnO4 into I minus, then you'll be able to see a reaction take place because this reaction is a spontaneous reaction. Okay? Okay, now as I already told you, because this is the revision notes, okay, so I can more or less explain in this way lah. So if you want to find out more detail, you can always go to my YouTube to find out more. Okay. 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 Any questions so far? Which part in here that you can understand? Would like me to repeat for you? Okay. So hopefully not much of a problem. Then immediately we goes to the next subtopic. The next subtopic is Nernst equations. So you must be able to memorize the Nernst equation. Either you memorize as E cell equals to E0 cell plus 0.059 over N. When it is positive, okay, when it is positive, it is reactant over product. When it is negative, it is product over reactant. And I always recommend students to memorize this one because when you memorize this one, you'll be able to apply all these four Nernst equation into these four respective way lah. Okay, okay, whatever lah. Okay, for me, it is better for you to remember the Nernst equation and in the negative form lah, because you can start to relate with the how to calculate standard cell potential. Okay, so for example, if your overall equation is 2Fe3 plus 2I minus give 2Fe2 plus I2, so when you apply your Nernst equation, E cell equals to E0 cell 0.059 over 2. 2 in here is the electron involved. 2 in here is the electron involved. So log, because this is plus, so it's plus, it is reactant over the product. So your reactant is Fe3 plus and I minus square and square, and then Fe2 plus is your product also square in here. So you follow the stoichiometry coefficients inside there. Okay. Okay, and then you can also use to calculate concentration cell. So for example, Zn2 plus to Zn2 plus 0.1. So in the concentration cell, E0 cell in here is going to be 0. In a concentration cell, E0 cell is going to be 0. Why? Because you are using the same species, just that they have different concentration. Okay, so I don't think any of the books that are available in the market will explain what is a concentration cell, but my module, Absolute Guide, have concentration cell. So if you want to find out more, maybe you want to take a look at my books there. Okay. Okay, so this is for the second application, and then Nernst equation can also be used to calculate Kc and also Ksp of cells involved. And then finally, Nernst equation can also use to calculate the pH of a non-standard hydrogen electrode. So that means your concentration in here is no longer equals to 1.0 mole per decimeter cube. So not only that you can use to calculate the concentration of the hydrogen ion, you can also use to calculate relate it with pH. Relate with pH. Okay. So for more examples, you have to go through my YouTube to see all the examples. In here, I just briefly discuss with you what is the important thing that you should know about Nernst equation. So try your best to memorize the Nernst equation. Very, very basic, very, very important. Okay. Okay, then we go to the next one. Okay, so this one is what we so call as the fuel cell. Okay, hydrogen oxygen fuel cell. I'm going to show you this one. Sorry. Okay, hydrogen oxygen fuel cell. So in this hydrogen oxygen fuel cell, actually you have two types. One is the alkaline fuel cell, the other one is acidic. So in alkaline fuel cell, you use potassium hydroxide. And then for acidic fuel cell, you use sulfuric acid. However, both of them are using platinum as the electrode, and their half equation for oxidation for acidic and alkaline fuel cell are also quite different. So in another word, when there is a questions that asks about fuel cell, you must be able to propose the correct oxidation and reduction half equation. Okay, and this diagram is also very important. So you must try your best to know at least how to draw a simple fuel cell. So this is a very simple diagram that you must be able to learn how to draw this fuel cell. The fuel cell STPM long time didn't come out already, and it has always been our syllabus for your information. So you must be able to draw the fuel cell and write the suitable oxidation and reduction half equation accordingly. Okay. Okay, so these are the half equations. So I hope that you can go through, and that is all for the fuel cells in here. Okay. Okay, then we go to the next one. Okay, so the next one is the electrolysis. So electrolysis is the process in which electrical energy is used to cause a non-spontaneous chemical cell reaction. It can only occur when electrolyte which contain free molten or aqueous solution having free moving ions. So what is an electrolyte? Electrolyte are a substance or molten or aqueous solution that have free moving ion. Teacher, have to memorize the, wait, teacher have to memorize the E value when explaining fuel cell or not. Usually in STPM, they will give you several half equation. So when they give you several half equation, you must be able to choose accordingly. Okay, yes, they will give you in the examination, so don't have to memorize. Okay, don't have to memorize. Okay. Okay, so back to our electrolysis. So inside electrolysis of the okay, inside electrolysis of the molten substance and aqueous solution in here, I can only generally describe like this. If you want to find out more, I'm so sorry, you can only have to go to the YouTube. But what I can tell you in here, inside electrolysis, anions goes to anode, cation goes to cathode. Okay, anion goes to anode, cations goes to cathode. Okay, so if it is in a molten state, very easy because there are no selectivity. So anion 2Cl minus will go to anode to undergo oxidation process. Cathode, which potassium ion will be attracted to, so it will undergo a reduction reactions in here. Okay. Okay. And then how to propose the product of electrolysis in here. So this is for aqueous solutions. So inside aqueous solution, not only there is an anion and cations of the species involved, but there also water is molecules surrounding the anode and cathode. So the half equation, therefore there will be selectivity. Okay, so this is the half equation of water at anode. This is the half equation of the water at cathode. So in here, at the anode half equation, the water is at the right hand side of the equation. Okay, and then for half equation for the cathode, H2O is at the left hand side of the equation. So why do we have to do that? Because eventually when we say we want water to oxidize, so you reverse the anode equation when it is being selected. Then you have to write the half equation accordingly. Okay, so let's say for example, if you are trying to electrolyze copper sulfate, let's say. Okay, so what are the species gathered at anode and cathode respectively? So you have copper 2 plus copper and water. Okay, since copper 2 plus copper is more positive, then copper 2 plus will be selected to discharge. Because at cathode, we choose the E naught value which is more positive or less negative to be selected. Okay, whereas at the anode, we choose the substance with less E naught value, less positive or more negative E naught value. Okay, so for example, if you have copper sulfate, so the sulfate in here positive 2.01 volt, water in here is positive 1.23. Because water is less positive, therefore water will be selected to discharge at the anode. So the product form as anode is oxygen, whereas the product at the cathode is the copper in here. Okay, so for more information, you can always refer to my other YouTube video. Okay, today is just an express revisions. Okay, to helps you to highlight what are the very important things that you need to remember. Okay. Okay. Wait, I see one question. Sir, the Nernst equation is only used for electrolysis of voltaic cell or chemical cell. Nernst equation is never for electrolytic cell. No, you won't have that. Okay. Okay, can. Okay, so that is for this one. Okay, then you must also memorize Faraday's first law and Faraday's second law. So Faraday's first law stated that quantity of the substance produced is directly proportional with the quantity of charge supplied into the electrolytic cell, whereas the Faraday's second law is the quantity of substance produced is inversely proportional with the amount of electron involved in the cell. So to apply Faraday's law, this is the fourth step. Q equals to IT, mole of electron is equals to Q over F. So then you compare using the half equations in here using the half equation, you compare the how many electron is to how many substance in here. Okay, stoichiometrically how many to how many. Okay, and finally, either you calculate your units in the form of the mass or the form of the volume also can. Sometimes it can be in volume. Okay. So for more examples, you have to refer to various examples that I've already prepared for you. Okay. Okay, so this is for the Nernst equation, so nothing much already. Let's move on to the next one. And then you have the rusting of iron. Okay, so showing to you in here are the important equation for the rusting of iron under acidic conditions. So these are the suitable half equation. Teacher, do we have to memorize or not? Because it is part of the syllabus, so by hook or by crook, if you feel that you are too lazy to memorize, then just know that which half equation should you choose for this one. Okay. And this is the under alkaline or neutral condition. So these are all the E0 values in here. Okay. Okay, so this is for the rusting process. And then in here, I've also helped you to summarize the extraction of aluminium from its ore, which is bauxite. Bauxite contain mainly aluminium oxide hydrated. So you have to first undergo purification via the following step. So you add with so first you add with concentrated alkali, where the aluminium oxide and silicon dioxide will react with the concentrated alkali to form the respective salt in here. Then you add either you add carbon dioxide, you add with weak acid to form the white precipitate of the aluminium hydroxide. And then finally you heat the aluminium hydroxide to become aluminium oxide according to these equations. Now once you get the pure this one, so you added cryolite. Okay, so cryolite is used to reduce the melting point of the aluminium oxide. Okay, to reduce the melting point of the aluminium oxide. So this is the half equation at cathode. This is the half equation at anode. Okay, and here are some description of the aluminium. So you must know that aluminium is a light metal which is naturally coated. This is very important. Naturally coated with an impervious oxide layer of the aluminium oxide that makes aluminium to be insoluble in water, resistance to acid-base reactions. So with all these good properties, so therefore it's essential to thickening the oxide layer. So the technique to thickening the oxide layer is called as the anodization. So at anode, aluminium is made as the anode of the cell. Aluminium is made as the anode of the cell, where in anode in here, oxygen is produced due to the selectivity. So this is the half equation of the anode in here. So the anode eventually will react with the aluminium to form the aluminium oxide in here. Okay. Okay, so these are all the suitable half equations that you must be able to remember inside this anodization process. Okay. Okay. Okay, so that is for anodization, nothing much already. And then this is chlorine. Diaphragm cell. Diaphragm cell, you must know the following thing. Your electrolyte is the brine, which is a saturated NaCl. Your anode is the titanium. So what is the half equation occur at the titanium? Where you have 2Cl minus gives Cl2 plus 2E minus. Whereas at cathode, you have steel. So the half equation is 2H2O plus 2E minus give 2OH minus plus H2. So at the same time, you also form some NaOH due to the Na plus react with the OH minus from the cathode in here. Okay. Also nothing much already lah. Okay, then you have this electrolysis of the copper. So electrolysis of the copper, where this is the half equation occur at anode and cathode respectively. So you must be able to explain why is it that the copper is oxidized at the anode of the cell. So based on the E naught value. So based on the E naught value, you have Cu2 plus Cu, SO2, S2OH2 minus, and 4H plus. So copper is the least positive. So because copper is the least positive, therefore copper is selected to oxidize at the anode in there. Okay, so that is why you see that the copper plate will decay will react away inside this electrolytic process. Okay, so there are actually quite a lot of applications that you must be able to remember in here. Okay, so with that, that will be more or less what you need to know about chapter 2. Okay, so these 2 chapters are compulsory to answer because every year STPM will definitely ask these 2 chapters. So either one structure, one essay, or both of them are essay. Because I never see both of them are asked in the structure now. Okay, so but still you have to study for both of these first 2 chapters because they are very, very important. Okay, so with that, that is how you should explain for electrochemistry. Okay, so nothing much really. A lot of calculations, a lot of things to apply that you must know inside here. Okay, starting from chapter 3 until chapter 7, all of them are memorized already. Okay, you have to keep on memorizing, keep on writing the equations until you can remember them by heart. Okay, so how are you going to do that? Let's start from the periodic table periodicity. Okay, so there are a few trends that you need to know starting from the atomic radius. So when going down to the group, so nuclear charge increase with proton number, screening effect also increase. However, effective nuclear charge also increase, that caused the atomic radius to increase. Okay, and when going across period of period 2, nuclear charge increase as proton numbers increase, screening effect remain almost constant because their electrons are filling in inside the same cell. So the repulsion between the electron and electron in the same shell is not significant for a lower shell. So as a result, the effective nuclear charge increase. So the atomic radius will eventually decrease. Okay, so I hope that all these graphs are able to help you to understand better how you want to explain your inorganic. Okay. And then this is the ionic radius trend. So ionic radius trend you as follow. So all of these ions are isoelectronic. So when they are isoelectronic, it means that they have the same number of electrons. Okay. Okay, so here are the things that you need to this one. So when they have this isoelectronic species, you must be able to find out and highlight. Okay, inside here. Okay, then the third one is the melting point. So as I already, the blue line in here represent group 2. I forgot to highlight. Okay, the blue line in here represent, the red line in here represent period 3. Okay, while the blue line in here represent group 2. Period 2, not group 2, period 2. Okay, so they can be generally categorized into 3 categories. So what are the 3 categories that can be categorized by them? So number 1, so this is the metallic bond. Okay, this is metallic bond. And then this is giant covalent structure. Okay, giant covalent. And then these are all simple covalent molecule. Okay, simple covalent molecule hold by weak van der Waals forces in here. Okay, so you must be able to explain accordingly. So for example, lithium and beryllium both form strong metallic bond where the metals ions are interacting with the delocalized C. So metallic bond inside the beryllium is greater than that of sodium, lithium, because beryllium has more valence electron. So greater the number of valence electron, greater the electron delocalized. Okay. And then you also must know that boron and carbon has a giant covalent structure. Okay, and then nitrogen, oxygen, fluorine, neons, especially neons, it is a monoatomic gas. While nitrogen, oxygen, fluorine are simple covalent molecule hold by weak van der Waals forces. So all of these things you must try your best to remember as fully as you can. Okay. Then same things goes to period 3. So period 3 in here, you have to know on how to explain what happens throughout the period 3. So for example, sodium, magnesium, aluminium is the metals because they are metal ion with delocalized C electron. So the metallic bond increase from sodium to magnesium and aluminium since the valence electron increase from sodium, magnesium, and aluminium. So greater the number of electrons delocalized, stronger the metallic bond. Then silicon in here has the exceptionally high melting point due to the silicon is a giant covalent structure. So you must be able to explain that also. Okay, P4 phosphorus, sulfur, chlorine, argon. In terms of the difference in here, okay, so chlorine has the lowest boiling point, followed by phosphorus, then sulfur, because of how their structure looks like. So chlorine exists naturally as Cl2, phosphorus exists naturally as P4, sulfur exists naturally as S8. Okay, so that is how you are going to explain one by one of them. Okay. Okay, so this is the melting point. And then showing to you in here is the ionization energy, electron affinity, and electronegativity. One thing that I would like to highlight in here is no matter which group that we are discussing in here, you must always remember that the fact in terms of ionization energy, when going down to the period, the elements from the period 2 will always be higher than the period group 13 under the same row. Okay, and then group 15 is always going to be higher than group 16. Okay, because of the row also. Okay. Okay, so this is how you are going to explain ionization energy and also this electronegativity when going down to the group and when going across period in here. Okay, then last but not least is the electrical conductivity. So in electrical conductivity, I only discuss about period 3 only because they have been stressing that too much. So when you are comparing electrical conductivity, between metal and metal, you use the number of electrons delocalized. In between non-metal and metal, you use the band gaps theory. So in metals, we say that this valence band and conduction band are overlapping each other, whereas semiconductor has a small gaps, which can be improved the conductivity by increasing temperature or by doping with phosphorus or boron. Okay, and then last but not least is this how are we going to describe the phosphorus, sulfur, and chlorine? Because they are all insulator. Okay, so this is for this one. Okay, then you also have to memorize all the equations when the group period 3 dissolve inside water. So 2Na plus 2H2O give 2NaOH plus H2. Magnesium plus H2O give magnesium oxide plus H2. Teacher, is the state of matter important or not? Not important. Don't have to write the state of matter. Doesn't matter. Okay. And then chlorine disproportionate inside water to form HCl and HOCl. Okay. And then the solution is acidic. Okay. And then what happened when sodium until sulfur, they burn with oxygen. So all these equations, try your best to remember. Okay. And then of course, there are acid-base properties and amphoteric properties of the aluminum oxide. So you must also try your best to remember. Okay, so no choice. You have to remember the equations. Okay. Okay, and this is what happens when these period 3 oxide are dissolved inside water. It will show acid-base characteristic. Aluminium oxide and silicon dioxide does not dissolve inside water. So this one you have to remember. Okay, and phosphorus oxide, sulfur oxide, and chlorine oxide, when dissolved inside water, they form an acidic solutions inside there. Okay. Okay, so period 3 more or less like that lah. Tak ada apa special sangat lah. Okay. Okay, then we goes to chapter, okay, sorry, there are one more. This is the reaction between period 3 oxide with the HCl and NaOH. So sodium oxide, magnesium oxide being a basic oxide can react with acid. Aluminum oxide is amphoteric, therefore can react with both acid and base. And then the silicon, phosphorus, sulfur, chlorine are all acidic oxide, so they can react with the alkali respectively, strong alkali especially. So these are the equation. So try your best to remember lah. Okay. Okay, then that is all for chapter 3 already. Okay. Okay, then we go to chapter 4. Now, no matter which group that we are talking about, atomic radius, melting point, ionization energy. So atomic radius trend, no matter which group that we are discussing, all of them decrease. So when going down to group 2, nuclear charge increase, screening effect increase, effective nuclear charge increase, not decrease. Can you help me to change? Effective nuclear charge increase. Not D, but E. Sorry, not decrease, but increase. Okay, therefore atomic radius increase. If you want to find out more, you can refer to the international reference books, or you Google by yourself. Why is it when going down to the group effective nuclear charge increase? Okay. Okay, and then melting point, beryllium, magnesium, calcium are hexagonal close pack. Barium, radium has open body center. Okay. Okay, then ionization energy also generally decrease. Nuclear charge increase, screening effect increase, atomic radius increase, effective nuclear charge increase, ionization energy decrease. Okay, so just remember the key points. Whatever that I highlighted for you inside the short notes here, those are the key points that you have to know on how to write. So you can eventually write a good essay if you remember all these important key points. Okay. Okay, then we have these are the inert values of the group 2. Showing increasingly negative means that they are stronger reducing agent. So beryllium does not react with water. Magnesium, calcium, strontium, barium react with water accordingly. So they form their respective oxide and hydroxide. Okay, and then the product form, beryllium oxide is amphoteric also. Calcium and magnesium is weak base, weak basic oxide. And then the strontium, barium are strong basic oxide. Okay, and these are the equations accordingly. Okay, and then the stability of the group 2 nitrate, you must also be able to explain the important point. So there are 7 important points that you have to explain whenever you are trying to describe about the stability of group 2 nitrate and carbonate. Just memorize if you don't understand. Okay, so stability of the group 2 nitrate and carbonate increase down to the group. Second point is you write this decomposition equation. Why is it decreasing? Why is it increasing? First, cationic radius increase, or you use the one with a smaller radius to explain. For example, beryllium. So you must say that beryllium has a smaller ionic radius, therefore beryllium has a higher charge density, therefore higher polarizing power. Therefore, high polarizing power of the beryllium ion is able to distort the electron cloud of the carbonate or nitrate ion. Okay, so this will weaken the CO bond inside the carbonate, hence forming a more stable BeO, because BeO is more stable than BCO3. Okay, and then last but not least, you have the solubility of solubility of the group 2 sulfate. Okay, so solubility of group 2 sulfate decrease down to the group. So you have to use enthalpy change of solution is equals to hydration minus lattice energy. So if since enthalpy change of hydration is greater than lattice energy, solution is exothermic, hence soluble in water. Hence, if hydration is lesser than that of lattice energy, enthalpy change of solution is endothermic, hence insoluble in water. So why does the group 2 sulfate solubility decrease? So start from the size of the group 2 ion increase. So both hydration and lattice energy decrease. However, hydration decrease more significant due to the large sulfate size. Okay, so just remember all these key points. Definitely you can write a very good essay on this. Come to this level, you have no choice but to remember the important key point. Okay. Okay, and then you also have the anomalous behavior in between beryllium and aluminium. So you must be able to describe the dimer property, the amphoteric properties of beryllium oxide and beryllium hydroxide, and then the hydrolysis. Okay, the hydrolysis. So all these notes that I summarized for you are the basic equation that you must know on how to memorize all this. Okay, so try your best, huh? Okay. Okay, so group 2 more or less like this, nothing much already. Okay. Okay, so okay, then we goes to the next picture. Okay, some of you started to ask, teacher, group 2 nitrate and carbonate compound is ionic or covalent? Ionic, all of them are ionic. All of them are ionic. Just that they are all ionic. Okay, they are all ionic. We are now just trying to describe why is it that the temperature required to break all of them increase going down to the group. Okay. Okay, what else? Nothing much already lah. So if you are able to compare all of them, write the equation, then you are very, very good already. Okay. Okay, then we goes to group 14, chapter 5, group 14. Atomic radius trend, melting point. Okay, atomic radius trend. Okay, pass. Okay, this one, melting point trend. So in melting point trend, you must be able. This is very important. Try your best to remember. Okay. Carbon, silicon, germanium are giant covalent structure. Okay. So why does the melting point decrease from carbon to silicon to germanium? This is due to atomic radius increase from carbon to silicon to germanium, causing the bond length between Cc to Si to Gg increase, therefore decrease the bond strength of Cc, Si, Ge. Okay, so in another word, since the bond strength decrease, so that is why easier to break. So that is why germanium has the lowest boiling point. Okay, so you must be able to remember that. Well, tin and lead are strong metallic bond. So lead has a higher melting point because it has a phase center cubic. Okay, and in terms of ionization energy, nuclear charge increase, screening effect increase, atomic radius increase, effective nuclear charge increase. Okay, however, there is a small anomaly in here where lead has a slightly higher first ionization energy compared to tin. Why? Due to the ineffective shielding of the 4f orbitals inside the lead. Okay, so that is why the effective nuclear charge are slightly higher, and that is why the lead has a higher first ionization energy compared to tin. Okay, and in terms of electrical conductivity, carbon as in diamond is an insulator because they this one. However, carbon is a graphite, is an electrical conductor because they are electron delocalized in between the sp2 hybridized layer. Silicon and germanium is a semiconductor because there is small band gaps in between valence band and conduction band. And then you must be able to explain the two factors that will increase the electrical conductivity, which is increasing the temperature or dope with boron and phosphorus. Okay. So that is all for the physical properties of the group 14. Okay. And then in here, you have to compare in between the oxidizing reagent and reducing agent. So these three standard electron potential is actually trying to tell you that when going down to the group 14, okay, so when going down to the group 14, the stability of the +4 oxidation state decreases. Okay, and at the same time, the stability of the +2 increase. Okay, so why is it like that? Why is it like that? This is due to the inert pair effect inside the 6s orbital as the energy level between 6N and 6P is too great difference. So don't have to explain until this far. Actually, the moment that you say why lead is more stable as a +2 oxidation state due to inert pair effect, then it's very, very good already. Don't have to this one. And then furthermore, with the increasing of the atomic radius, it causes the ionic characteristic to increase, okay? Causing +2 oxidation state to be more ionic than more stable. Okay, so that is the reason why lead is more stable as a +2 oxidation state. Okay, and then you also have a very, very small subtopic called as catenation. So catenation is the ability of elements to form bond in between two or more similar atoms using covalent bond. So the catenation decrease, bond length increase, bond strength decrease. Same factor. Okay. Okay. Then now, these are the very important key points that you must be able to write down when you are trying to explain the oxide of group 14 element. No matter what, when you want to write essay describing the oxide of group 14, you must always start off with like this. Group 14 elements has the valence electron of Ns2, Nb2. All group 14 elements exist as two types of oxide, namely group 14 monoxide, MO, where M in here has a +2 oxidation state, and then also MO2 dioxide, where M in here is +4. This is the most important statement whenever you are trying to describe about. There are two things that you need to describe. Either you are going to explain the stability of MO and MO2, or you are going to explain the acid-base property of MO and MO2. Okay, so let's say if you want to explain the stability of the MO and MO2, you must say that stability of MO increased down to the group 14 as +2 oxidation state stability increased down to group 14. So for example, CO2 is more stable than CO according to the equation 2CO plus O2 give 2CO2. So in +4 oxidation state, group 14 elements are bonded to oxygen covalently. However, the strength of the covalent bond become weaker as the atomic radius increase, so decreasing the stability of the +4. Whereas in the other hand, +2 oxidation state changes from covalent to ionic. Therefore, PbO is more stable than PbO2 according to the equation. So 2PbO2 will form 2PbO plus O2. Why is PbO2? Why is Pb more stable as a +2? Just due to the inert pair effect. Okay, so these are all the key points that you try your best to write down whenever you're trying to explain the stability of MO and MO2. Okay. Whereas when you are trying to explain the acid-base property of MO and MO2, so you generally say this, basicity of the oxide increase down group 14 oxide due to the ionic characteristic increase. Okay, then you have to try your best to remember all these points. Carbon monoxide, silicon monoxide are neutral oxide. Germanium oxide, tin oxide, lead oxide are amphoteric. And when you say that they are amphoteric, then you have to write the equation. Most of the time, this kind of question, they just ask you to describe the reaction. So when you are asked to describe the reaction, just describe with the proper equation. So this equation is a general equation that is accepted. Okay, so just remember all these equations already. Very good already. Okay, okay, and then this is +2 oxide. Then +4 oxide, CO2 and SiO2 are acidic. So you just write any of the equation, they are the same. And then GO2, SNO2, PbO2 are amphoteric. Okay, so when act as a base, when act as a acid, you have to write the equations accordingly. Okay, so these are the very, very important key points that you must try your best to write out whenever you are trying to describe about the acid-base properties of the MO and MO2. Okay, so that is all for the group 14. Okay. Okay, then we goes to the chloride of group 14. So whenever you are trying to describe the chloride of the group 14, so all of them has the formulas MCl4. They are all simple covalent molecule held by weak van der Waals forces. Three things that you can use to describe inside the chloride of group 14 include their melting point. So generally increase when going down group 14. Why? Because they are simple covalent molecule held by weak van der Waals forces. So van der Waals forces are influenced by the relative molecular mass or molecular size. So as the molecular mass or molecular size increase, the strength of the weak van der Waals forces increase. That is why the boiling point increase. However, CCl4 has exceptionally higher boiling point due to the small size of the molecule that gives the strong intermolecular forces. Okay. Then the second thing that you need to explain for the chloride of group 14 is the stability, thermal stability of MCl4. So stability of the MCl4 decrease when going down to group 14. So why is it like that? Because they are covalent compound, isn't it? So when they are covalent compound, they are whole by covalent bond. So as the atomic radius increase, bond length of MCl increase, bond strength of NCl decrease. So that is why they got easier to dissociate. So tin 4 chloride and lead 4 chloride can decompose to become SnCl2, PbCl2, and Cl2 respectively, according to that equation. So in other words, in terms of stability of the group 14 chloride, carbon, silicon, germanium are more stable as +4. That means they are stable as CCl4, SiCl4, GeCl4. And then for lead, they are more stable as +2. That means SnCl2, PbCl2 are more stable. Okay. Okay, so this is the second thing that you need to know for the description of the group 14 tetrachloride. And then last but not least is the hydrolysis of the group 14 tetrachloride. All group 14 tetrachloride can undergo hydrolysis to form MO and HCl, which is a white film, according to the equation. MCl plus 2H2O give MO plus 4HCl. Only carbon in CCl4 cannot undergo hydrolysis. Why? Because you does not have empty d orbital. Okay, so this is the only explanation that you have to try your best to understand. Okay. Okay, then that is for the hydrolysis. Okay, I got questions in here. Okay, some of you ask, sir, for thermal stability, can use inert pair? Yes. Another reason that why lead is more stable as PbCl2 also due to inert pair effect. Yes, you have to also write that down. Pardon me because I didn't write that down. In fact, actually, you have to write that down. Okay. Okay, so with that, that is for group 14 tetrachloride. Okay. Okay, then the next one is the silicate. Now, silicate, I'm going to highlight only these three because throughout all the passing question, only these three are stressed. Try your best to remember the characteristic of them. So, pyroxene, amphibole, and silicate sheets. So, pyroxene is the single chain silicate. Amphibole is the double chain silicate. And then silicate sheets is the silicate in the two-dimensional form. Okay, so you must also be able to explain how many oxygen atoms are shared per molecule. Pyroxene share 2 of its oxygen atom. Amphibole should share 2 or 3 oxygen atom. And then the silicate share 3 oxygen atom. And then you must also try your best to at least remember for amphibole and silicate sheets, what are the example of application. So amphibole examples is asbestos, silicate sheets is talcum and kaolin. Okay, so these are the things. So teacher, do we have to memorize the structure or not? No need to memorize, but you should at least know how to calculate the repeating unit. Okay. So that is what is stressed in here. Okay. So only remember these three, enough already. The rest, never mind. And then silicon, this one, it has always been part of the syllabus, but never been stressed in STPM. I'm so worried that it will come out, even though it is a very small subtopic. So inside my short notes here, I just highlight the important points. So silicon is a group of polyorganosiloxane containing SiC long bond. Okay, so more important is the properties of a silicon. So R inside the silicon is hydrophobic, therefore insoluble in water. Oxygen inside the OSiO can form hydrogen bond with fabric, so makes the fabric waterproof. That means when you apply silicone towards that fabric, it causes the fabric to become waterproof due to oxygen form hydrogen bond with the fabric, and then the alkyl outside there prevents the water from penetrating. Okay, so it can be cross-linked to make the silicone harder and can withstand heat. So some of the okay, wait, I have a question. I should scroll back. Teacher, can for drawing the silicate, we label the atom as well. Yeah, the black dot, the white dot inside here, the white dot represents oxygen, the black dot represents silicon. If you want, go ahead, label. Okay. Okay, can I? Okay. So application used in the form of fluid silicone for lubricant. It is also used in waterproof fabric. And then silicone is in the form of rubber, can convert to elastomer. Okay. Nothing much already. Okay. Okay, then we have glass. Glass is an amorphous solid, does not have a regular three-dimensional arrangement. So, and then just remember this three lah, enough already lah. STPM 2006 last time, they asked about these three examples. Okay, just remember one or two properties, then enough already lah. Okay, that's why I said that in organic chemistry, a lot of things should be memorize. So you have no choice but to memorize all the things that I described to you in here. The best way to memorize is to write back what I shows you in here. Okay. Okay. And last but not least, this one is the tin alloy. Tin alloy, try to remember these three alloy. Bronze is made of copper and tin. Pewter is made of tin and lead. Solder is also made of tin and lead. Don't have to really memorize the percentage, but at least memorize the alloy that makes them, okay? And what is it used for, okay? The applications are. Okay, so with that, that is for chapter 5. And then for... okay. Okay, then we have chapter 6, halogen. Okay, for halogen, chlorine, bromine, iodine, you must be able to describe their physical state. Chlorine is a yellow-greenish gas, bromine is a reddish-brown liquid, and then iodine is a purplish-black solid. You should also be able to memorize the color of the halogen in the aqua solution and also in CCl4. Chlorine in aqua solution is pale yellow, bromine is brown, iodine is also brown. Okay, in CCl4, chlorine is colorless, bromine is brown, iodine is purple. So you must try your best to remember this one. Okay, so that is for physical properties and what is their solubility lah. Then you also have to describe the displacement reaction with the ion. Okay, and of course you have to learn how to describe the displacement in between halogen and halide ions. This one inside my short notes I didn't include, so you include by yourself later lah. Okay. Okay, so inside here, chlorine and bromine can act as an oxidizing agent, but iodine cannot. In fact, iodide ion act as a reducing agent. Okay, iodide ion act as a reducing agent that reduce Fe3 plus to become Fe2 plus. Okay. Okay, then you also must try your best to remember the reaction of halogen with chlorine under different conditions. No. Colorless. Some of you ask, teacher, my reference book says Cl2 in CCl4 is pale yellow green. Refer to, you search YouTube lah, search online lah. My method very easy. If you are not sure, you find contradiction in between here, find online. Nowadays everything is convenient. Search online. Okay. But I have the confidence to tell you that CCl4 is colorless in chlorine. Okay, and these are the equations that you have to memorize when especially chlorine. Chlorine behave very differently when dissolved in cold NaOH and hot NaOH. So try your best to remember the equations. Okay, must be balanced. Oxidation state must also be written. Okay, try your best to calculate the oxidation states. Okay, and last but not least is the reaction with water and the reaction in S2O3. Now, for this is especially important. The reaction in between the thiosulfate with iodine is especially important. So try your best to remember that. Okay, that's why I highlighted them in a different color in here, so that you will take notes a bit. Okay. Okay, then now these are the hydrogen halide HX in here. So HCl, HBr, all of them are actually white film. All hydrogen halide are white film. The reaction with the halogens with hydrogens is the one that shows how reactivity they are. Chlorine is the most reactive, followed by bromine, and iodine is the least reactive. And then in terms of bond energy, we say that bond energy decrease from HF to HI because of the atomic radius. So atomic radius increase, bond length increase, bond strength decrease. Okay. And in terms of acidity, HCl, HBr, HI are strong acid. HF is a weak acid. Okay. And then in terms of preparation in laboratory, this hydrogen chloride is prepared by reacting with concentrated sulfuric acid. Okay, so you form the white film of the HCl, whereas HBr and HI is prepared by the hydrolysis of PX3. Okay, because this sulfuric acid will further react bromide and iodide ion, which is explained inside the next slide in here. Okay, so these are all the slide. These are all the very important key points when the halide ion react with the silver, followed by the reaction with ammonia. So chlorine is white precipitate, bromine, AgCl is white precipitate, AgBr is cream precipitate, AgI is yellow precipitate, AgCl is soluble in dilute and concentrated ammonia, AgBr only dissolve in concentrated ammonia, and then AgI does not dissolve in ammonia. And then you should also be able to observe what happens when the H2SO4 react with the I minus, Br minus, and Cl minus. Okay. Okay. Then you have to also explain what is their properties. H2SO4 first act as a Bronsted lauric acid, but it cannot further oxidize chloride ion to become chlorine because H2SO4 is a weaker oxidizing agent than Cl2. But H2SO4 can further oxidize Br minus and I minus because they are a stronger oxidizing agent. Okay, and try your best to remember all these equations. Okay, this equation must be memorized, no choice. Okay. Okay. So with that, that is all for the halide ion. Okay. Okay, so that is all for group 17. Nothing much. Okay, and last but not least, D block element. Now, D block element, if you can understand very good, cannot understand, then just remember some simple one enough already. But inside the short notes here, I already highlighted some of the very important points. You must know how to define transition element. So what is a transition element? So transition element is defined as element that can form more than one stable ion with an incomplete electronic configuration in inner 3D orbital. Okay, and here are the traits of the atomic radius, melting point, and ionization energy. In terms of atomic radius remain almost constant. Why? Nuclear charge increase with proton number. Screening effect also increase because electrons are filling inside inner orbital. So effective nuclear charge remain almost constant as the increase in nuclear charge and screening effect cancel off each other. So if you cannot understand, then just remember the important point. Some of you ask, teacher, do we need to memorize the application of photography? You add by yourself lah. Actually, very small subtopic only lah. Okay, you add by yourself, can, no problem. Okay, and then in terms of melting point, D block elements are held by strong metallic bond. Usually melting point we don't compare inside the transition element. We compare with the main group elements group 1, group 2, group 13. Okay, so generally all group transition element is a higher melting point compared to main group metal because they have more delocalized electron, therefore has a greater metallic bond strength. And then in terms of first ionization energy, also the trait also more or less the same with the atomic radius. Okay. Okay, so this is the physical properties, slightly a little bit different from that of the main group elements. So try your best to distinguish them. Okay. Okay, and then the transition element has 4 special chemical properties, exhibit more than one oxidation state, can form coordination compound, form colorful ion, can act as a catalyst. Okay, so most of the transition element exists as a +2 and +3. So which one is more stable? Early transition metals, transition elements are more stable as a +3 oxidation state, highlighted in the purple color. And the later part of the periodic table are more stable in the +2 oxidation state. So this can be explained from their E0 value inside here. Okay. And then you should also be able to explain the reaction of the M2 plus in acidic air. So the spontaneous reaction in here include Ti2 plus, V2 plus, Cl2 plus, and Fe2 plus. When I say that spontaneous reactions, that means Ti2 plus, V2 plus, Cl2 plus, and Fe2 plus can be oxidized by air. Okay. Whereas stability of the M3 plus in aqueous solutions, spontaneous is Mn3 plus and CO3 plus. That means when dissolved inside water, Mn3 plus and CO3 plus eventually will be reduced to become Mn2 plus and CO2 plus. Okay. Okay, so that is the thing. And then coordination compound, try to remember all this definition. How do you define coordination compound? What is the definition of complex ion? What is the ligand? What are the type of ligand and their name as the ligand? And then here are the 4 step-by-step of how you name them. Like I said, if you can name very good, cannot name, then never mind. I'm just worried that they come out in structure. So if they come out in structure, then no choice. Okay. So sorry you have to refer to the YouTube. This one is just as a revision express notes. So okay, I cannot explain everything in this short 2 hours. Okay, but this one is you must be able to define why is a complex colorful. Why is a complex colorful? I highlighted in the red color in here. D orbitals experience electrostatic repulsion. 5 degenerate d orbitals split into 2 different set of energy level. So when white light pass through, color is absorbed in the form of wavelength and energy. So when this happens, DD transition take place. Okay. So these are the few important highlight points that you should be able to write in your essay. Why is a transition metal colorful? 3 very important key points is especially d orbitals split into 2 different energy level. White light pass through, energy absorbed, DD transition take place. So these are the 3 very extremely important key points. And then if the d orbitals are empty or complete field, so there shall be no DD transition. Therefore, the solution is observed as a colorless solution. Okay, and then these are what color absorbed is observed as what color. This one only 1 mark only but I include a little bit inside the notes. Okay, and then these are catalysts. Catalysts, you have to memorize these 2 only Okay, so if you can remember, very good Cannot remember, then never mind what to do, because a lot of things, transition element, a lot of things. Okay, so I just put inside there. You try your best to remember Okay, and then application, nothing much really Okay, so before I end the live stream, any questions? Okay. Teacher, I'm confused when central atom in ammonia aqua solution, sometimes complex form is aqua and sometimes is amine. I don't quite get what you try to ask in here. Meaning what? Can you be more specific, please? I cannot understand. Sorry. Aqua and amine, this one are more to ligand. Okay. To be honest, I don't quite get what you're trying to say so I cannot explain very well. Can you be more specific? Okay, what else? Before I end my live stream today. So I'm so sorry at this very last minutes. That is what I can do my best to help you all. So I wish you all good luck in your semester 2 ulangan tomorrow. Answer I will do tomorrow. Okay. How to calculate coordination number? Coordination number is based on how many dative bond. If you have to look at the complex. You have to look at the complex. If the total, like in here, you see, monodentate is 1 ligand, bidentate is 2 ligand. So summation of the ligand attached to the molecule, let's say if you have this following formula, there is one question that I asked in our trials. It says that what is the coordination number for CO NH3 EN2. So what is the oxidation number and what is the oxidation number and the coordination number? Oxidation number, you calculate CO in here is +2 Okay, oxidation number is +2. Coordination number, because CH3 is a monodentate ligand, ethylene diamine is a bidentate ligand. So monodentate means 1 So 1 times 2 plus ethylene diamine, this is the ethylene diamine. You have 2 ligand you have 2 ligand per molecule So 2 times 2. So therefore, coordination number in here equals to 6. Okay, so that is how we calculate coordination number. Okay. Okay. Just now the Ren Huai tried to ask, like, why sometimes the ligand is water molecule even though center metal ion is in ammonia aqua solution? What? Terbalik I've seen. Initially water, then become ammonia I've seen, copper, for example. So the blue color of the copper aqua solution become dark blue solution when you added ammonia. Because ammonia is a stronger ligand than water. So for the strength of the ligand, if you search Google, if you have my book also explain what is the strength of the ligand. So you follow the strength of the ligand to see whether a ligand can displace the other ligands or not. Okay, so that's what I can say to you. Okay. Okay, welcome, Jingning. Okay, what else? Okay. I don't see any more questions. So I guess that is all for my live stream today. I hope that you all benefits from it. Good luck for your tomorrow SEM 2 ulangan. And to those who will be sitting for trial examination, does magnesium react with cold water? No, magnesium does not react with cold water. No lah. Magnesium only react with steam only. Even water also cannot react. Don't say cold water. Okay, cannot. Some books say yes. No. Hey, you Google, you YouTube have that. Try to see YouTube. Okay. Some books say yes, some books say no. I said no. No lah, don't. The answer is no. Okay. Do we need to memorize the strength of the ligand? No need. Actually, need to memorize. Don't. Hey, I rather you memorize some more important things, Okay, I rather you memorize more important thing rather than the strength of ligand. Strength of ligand only 1 mark only, so don't need to memorize that, Vanessa. Okay, no need. Okay, welcome, Wenxuan. Okay, so I think I guess that is all for our streaming today lah. Good luck lah. Okay. So I wish you all the best lah. You all can do it one lah, no problem one lah. Okay. See you all next time. Bye.